Nice talk, Shubhendu. Good talking after you, and you have covered good ground in the PROTAC. So you have already introduced it, so it's only part of my talk. But mainly, I'll be talking about the 4D docking. And before I do this, it's not just customary but also important to congratulate Advent and Surojit for his. He has been telling me for last 2-3 years that he wants to conduct a UGM, and I think it's really congratulations to you and your team that you could finally pull it off and call in the first UGM. So okay, at least try to make it a biannual event, and it's good because room full of people, and I'm sure it's only going to increase, right? Probably going forward, we can exchange, more critical notes on how we use this software and how we can actually benefit from that. So, in terms of using ICM itself, and of course, I want to because I talk about the learning curve. So it's very important to thank Andrew Ori, because a long time Schrodinger user that I was, first time I encountered ICM, it was like I didn't know driving and I was on a highway. So Andy's hand-holding helped us to scale that mountain, and finally we have some sort of communication with ICM, and with their sparse documentation. That's important. Okay, so that's going to be my talk. I'm going to talk about 4D docking, which takes the protein flexibility into account, or as much as we can take it into account. And I will briefly touch upon the APF molecular, which in my opinion is very critical molecular recognition tool that we have. And I will briefly talk about PROTAC modeling, because I'll be outdated otherwise, right? Then some requests to the Molsoft team itself. So what is the importance of 4D docking? 4D docking is important because the ligand binding sites in the protein are not optimized for ligand binding, but they are customized for the binding of a particular ligand. The protein side chains adopt that small little different conformation to accommodate that particular productive binding of the ligand in question. So, which through normal docking methods we have not been able to capture that very effectively. So that's where I feel one of the key advantages that 4D docking actually brings for us. It's everybody's experience. Docking critically depends on the choice of the crystal structure that you use. If you were to use a wrong structure, even the most potent compound would not actually model, right? That's everybody's common experience, I think. So therefore, in my opinion, the 4D docking is the closest we come to considering the protein flexibility. There are other tools. I am not discounting that. I am aware of that. I have used them also. But the beauty of 4D docking is it does so in a high throughput manner. Okay, you are actually able to screen large databases on a 4D grid as efficiently you are able to do on a single docking grid. Okay, so that high throughput being the keyword here. And I'm going to at least show a case study. That's not necessarily a case study we did with any client or anybody, but it's more of a demonstration case study, something like what Mohsin would do to showcase to his clients. I would made your job easy. Okay, so we can take it forward and probably do it in a more elaborate manner. So it is likely to enhance the hit rate. So I have used IRAC4 as a case study. Why IRAC4? Not necessarily because of its biology or anything. I am not going to talk about it. Not talk the biology of it. But IRAC4 has been a part of my life for a long time. Okay, and since it is something that whatever results I get, I can easily eyeball and know whether it's right or wrong so quickly. So it helped me to put together this case study in a reasonably quick time. And there was availability of sufficient amount of data in IRAK4, so that's the reason I chose IRAK4, not so much for its biology, or which is of course important. Okay, so therefore you would have understood by now what I am going to do. I am going to construct a 4D grid of IRAK4 and then model a bunch of compounds. But here is the problem statement that I did, and the way I chose my data set is like this. So there are 59 co-crystallized ligands that are available for IRAK4. It's a pretty good data set, that as good as you have. Okay, and so you don't want to take 59 structures into a 4D docking grid. Okay, so what I did is I chemically clustered the 59 compounds, and this particular slide shows you the different colors belong to the different clusters. Okay, so based on the chemical similarity, they actually belong to the different clusters, and I don't know how clear it is. It's not at all clear to me what's going on here. Okay, these compounds have pretty similar motifs. Okay, so they are actually classified into the same grid, same cluster. Okay, so these structures actually, they included very distinct hinge binders. I am sure a lot of people here work on kinases and know the importance of the hinge binding motif. So these these different clusters actually represented different hinge binding elements, and they span the different regions of the binding site. Okay, so therefore I feel it's a pretty reasonably chemically diverse group to have. So next, what I did, so there are I chose from each of these cluster. There are about some 30 odd clusters, or around 25-26 clusters, I think. From each of these clusters, I chose the highest resolution structure. Okay, so that is what was going to constitute my 4D grid. Okay, so these are the compounds that were chosen, whose complexes were actually chosen for the to construct the 4D grid. Okay, they all belong to distinct clusters, as you can see in this particular plot. Oops, what is this? Okay, yeah. This is what is known as the similarity plot. Okay, that actually shows you the compounds that I chose are reasonably distinct. Okay, so they're pretty spread out on the similarity plot. Things are falling around. Okay, so you can see particularly two things here. There is a type 2 ligand that is here, ponatinib. Okay, I am sure experienced campaigners can identify type 2 ligand by looking at it, right? You also see I have highlighted the top row, also one of the compound, because that's the compound I modeled, and okay, that's a BMS chemotype, I am one of the co-inventors of that series of compounds, including the other compounds. So what I did is I took, I constituted a 4D grid using all these 26 structures. So from 59 we reduced to 26. Of course, we could reduce probably more. Okay, but it is an exercise in data reduction. Okay, so how many fewer structures you can take to get this kind of thing. And I am not saying that this is the only way to do that. I did the best data reduction here, but I am just showcasing one of the ways of doing the data reduction here. And this is the 4D grid that you see. Another beauty with ICM, just go right click, export as movie. We absolutely love it. Okay, so what you can see here is if this is the DFG loop that you are seeing here. Okay, and if you notice that, so you can see that there is one of the DFG out conformations is also part of the docking grid, or the part of the 4D docking grid. Okay, so these are the unique chemical classes, so which actually constituted the 4D grid. So putting the workflow together here, what I did is the leftmost, first you query the PDB, everything in the ICM. Okay, like Ruben was telling in the morning, I might be looking like an ICM spokesperson here, but you know, that's not the idea. Okay, it's just that it enables your life, so it makes your life so much easier. You don't have to go, you know, look at it in the RCSB, then do something else. So I just looked at the you know, the IRAD4 structures, pulled down the structures, did the ligand clustering, 4D grid generation, and 4D docking, then the hit retrieval rate. So I am sure you are thinking ahead of me, and what I did is, into this 26 complexes 4D docking grid, I modeled all the 59 compounds. The idea is to retrieve all the 59 binding modes from this particular 4D docking exercise. Okay, that's the only idea. Very simple experiment. I don't think it took me just 1.5 days to do the work as well as make this presentation. Okay, so but I just wanted to, especially for the young modelers, I want to put together a way of, you know, how you should be critically thinking about what is the in silico experiment that you are actually doing here, right, and why you are doing it. So while trying to understand the 59 different the docking modes, one of the things is the charge state of the ligand in the at pH 7 is absolutely critical. We know that, right? This is where, Mohsin, you should take notes. ICM's pK prediction needs to improve. Okay, learn something from the other thing, like Chemexon does a much better job. Okay, if you can do that, well and good. But I think I want you to take note of this, because what happens in especially kinases, when you have a heterocycle binding at the hinge region. Okay, now if you have inappropriate protonation that happens there, the acceptor becomes a donor, and you no longer make the hinge interaction. Okay, so that is why when I actually did the you know, the auto, I ran the docking in the auto mode. Okay, it actually gave me very poor enrichment. Okay, then the next thing that I did is, okay, I didn't want to do the auto mode, but at least there are a bunch of piperazines and all that. People who are again familiar with the kinase space, they know that we stick out a piperazine or some in the solvent group. Okay, so which gets protonated, obviously. So I manually protonated those. Okay, and when I manually protonated those, you know, the my hit rate, you know, the kind of enrichment of the binding modes was actually not really great. Okay, not. In fact, I didn't like many of the binding modes. Okay, it was not doing a good job of predicting that. So, which is where okay. So this actually shows you. Okay, this is the distribution of the scores that you had. Okay, of the top docking mode. So I docked the 59 compounds and chose the binding modes manually from each one of them, for each one of them. Okay, and you see the distribution of the docking scores. Most of them were greater than -30. Okay, few of them were between -30 and -35, and you know, the top the compounds which docked better than that, which scored better than that, were actually fewer. That left side one shows you which of the receptor conformations that were picked most frequently. Okay, so the blue one actually shows you the all modes. Okay, in fact, including the you know, the not so good modes, because 10 per ligand, so we had about 590 modes. Okay, so out of that, if you see this conformation, this receptor conformation 11 was actually picked more than 200 times. Okay, there is a reason for that. A lot of I hope you can make out that middle structure where you are seeing an amide as the hinge binder. Okay, so the amide being the hinge binder, that is where I mean, most of the reported IRAD4 inhibitors have that, including your compound, right? Yeah. So therefore, those compounds are picking that particular conformation repeatedly. Okay, so that's what happened, and what you see in red are the bioactive conformations. Even they pick that particular receptor conformation 11 a lot. But overall, I actually saw poor docking modes a lot of times, so I was not too encouraged by this one. So the charge consideration was actually not helping. So that is where I moved to dock the neutral species as it is, although like you might not, in this case, remember we are doing a virtual screening type of exercise. The idea is not to get absolutely right binding modes which you are going to optimize, but rather to pick whether you are able to identify a hit as a hit or not as a hit. Okay, so that since, so therefore I actually took this particular route and took the neutral species. And when I took the neutral species, still the same conformation actually picked up. I already explained why. But you see there is a dramatic improvement in this scoring. Okay, there is a left shift in terms of the population which has actually scored better. So this reflected in the docking modes also, and I could actually pick good docking modes for most of the compounds, for in fact all of the compounds. Okay. This shows you a sample of the different docking modes that I actually picked. So you see the leftmost, the amide being the hinge binder. The middle one is where you have a quinoline as the hinge binder. The right side is the Pfizer chemotype. The top right side is the Pfizer chemotype. Okay, that has a primary amide as the hinge binder. The bottom left is a type 2. Okay, so it actually picked up the type 2 ligand, picked up the type 2. So you can actually see that the DFG conformation, the DFG in the out conformation here. Okay, the bottom middle is the BMS chemotype I worked on earlier, and the bottom right is the Nimbus chemotype. So suffice to say that across chemical class, this 4D grid actually, I just showed you samples, but in fact every one of the 59 modes actually could be reproduced. Okay, I didn't go into RMSD, but again that was not my idea here, to show that we are exactly getting a crystal structure like RMSD, because RMSD becomes very important in a lead optimization. When you are trying to hit to lead or a lead generation, lead optimization, that's when RMSD becomes very important. In this case, I am just trying to not miss out any potential hits. Okay, that's my whole idea of this particular thing, right? So then I tried to do an analysis here. Like in this particular plot, you are seeing the x-axis is the chemical cluster. Okay, the number of the chemical cluster, and the y-axis is the receptor conformation to which chemical cluster the receptor. So in the x-axis you have the chemical cluster, the representative of that particular chemical cluster that picked up a certain receptor conformation. Okay, to which chemical cluster did the receptor conformation belong? So ideally, if every chemical cluster picked the receptor conformation it belonged to, you would have a pretty good diagonal line where all the points would stack up along the diagonal. Okay, but in this case it is not happening, it is actually spread out. Okay, which means that compounds, although they are showing you good docking modes, they are picking up members of other clusters. Okay, that's okay as long as you get a good docking mode, you are reproducing the binding mode. Okay, and in the bottom you are actually seeing some of the examples of the left hand side is the compound which is modeled, and that modeled into the right hand side, so into a grid that actually contained this compound. Okay, so the staurosporine bound into a compound that contained this one. Okay, so this is just a sample of out of the 59 ligands, how some of them actually modeled. So I will summarize this particular effort on the IRAC4, where I am saying that all the compounds, they reproduce the crystallographic binding modes in the first or the second mode. Okay, although I asked for 10. Only in the first or the second mode we could actually get the crystallographic binding modes, okay, or close to that. Okay, 8 compounds picked the exact structure they were complexed with. Okay, which means they exactly lie on the diagonal on that particular plot. Okay, 8 compounds. But if you have noticed the way the chemical clustering works, usually successive clusters will have very similar compounds. Okay, that's because of you can adjust the distance of the cluster, and they usually belong to the same tree, okay, or the same branch, right? So, so therefore, I could take the difference of 1 or 2 in the chemical cluster numbering to say that they probably belong to they have modeled into a cluster that has a similar compound. Okay, so that is what the red diagonal lines actually indicates. So in that particular band, okay, you actually found 34 compounds. Okay, so while 8 compounds pick the exact cluster that they belong to, about 34 compounds they modeled in actually clusters which were close by. Okay, thus what I say is there is a significant enrichment which cannot be achieved by considering any one of the PDB for docking. Okay, so this is my take home message for you, that if you were to choose one compound out of 59, okay, one structure out of 59 structures, okay, and I am pretty sure I can give it to you in writing that you will not get the binding mode for all the 59 compounds in that. So extrapolate it to a virtual screening scenario where you are trying to get virtual hits for your compound. So it is actually that much more likely to improve your hit rate. So therefore, my proposal is that this can be a general method for virtual screening. Okay. Now you can ask me, I will not have 59 compounds, 59 structures to choose from in each case. You should be aware of some other ways of finding, conformational variations of these structures, so that you can basically put efforts to generate your 4D grid in such a way that you are not likely to miss out anything. Okay. Now, I am very fond of saying this. If you encounter a protein down the corridor, okay, might sound like sci-fi, but because our very normal representation is like this. Okay, we show the chemical compound. I am done with IRAC4 case study, by the way. Yeah. So I'm briefly touching upon APF because I feel if ICM were not called ICM, it would be called APF, because it's I think that's the closest we get to molecular recognition, because we are very fond of representing things like this, in ribbons, in compounds, in sticks, and all that. But that's not how molecules will see each other, right? Molecules will see each other like this, okay, where they are actually surfaces that contain charges and all that. And yeah, that's what I mean by, that's a ChatGPT image. Okay, if you were to meet a protein in a corridor there, that's what that guy would look like. Okay, yeah, obviously it has been blown up billions of times, but so that is where I feel APF is the closest we get to molecular recognition. Sorry, that should be molecular recognition, not modeling recognition. Sorry. Okay. So where you see the ligand surface and the protein surface actually being complementary to each other, and the way it actually runs behind in the APF clustering or the virtual screening is something that I am a big fan of. Okay, in ICM. Okay, and that's been, I think, utilized pretty well. Okay. Yeah. So finally, this is not the summary of my whole talk, but I will be done in next 10 minutes, stand between you and lunch. So, okay. As I said, if I don't talk about PROTAC, I'd be, I'll look outdated. So we also did something on PROTAC, but we didn't quite use the PROTAC script in this particular case that ICM advocates a lot. But in this case, we went from a bottom-up approach, okay, to answer Raghu's question of are there any other ligases that people consider. Yeah, you do see off and on reports of other ligases which people use. In this particular case, there is a ligase called RNF114. Okay, this work is done by my colleague Hemant, and I am only presenting it. So there is this ligase called RNF114. Okay, which has a covalent cysteine in its binding pocket, and there is no structure actually reported for RNF 114. So and this group actually they reported an inhibitor called EN219 based on which could bind to this RNF 114. So what we did is we took the alpha fold structure. No matter how much Ruben hates it, alpha fold is here to stay, and a Nobel Prize has legitimized them even more so. Okay, so we took the alpha fold structure of and it's a zinc binding protein. Okay, it contains zinc fingers. So we used another protein structure, RNF 125, to bring the zinc back. Actually, this was the time when alpha fold 2 and 3 were not there. So, we actually did pure grafting business to bring the zincs into the right places and then do our classical modeling. And that's how we came up with the RNF 114 structure that was zinc bound, and we clustered the trajectory. Then we actually, modeled this the EN219 RNF 114 complex onto the BRD4, the RNF 114, the protein-protein docking. Okay, so that is the ligand. That's what the ligand looks like. If you are that left side structure must be all too familiar to PROTAC guys. The BRD4 is I don't know, that's like the carbon of PROTAC modeling. Okay, everybody uses it, not modeling, actually PROTAC experimentation. So that is actually bound to this particular RNF 114 ligand EN219 that has a chloroestamide that you see here, which is the warhead that traps RNF 114. So we actually took these structures individually, the alpha fold structure of the RNF 114 with the EN219 modeled into that, and we took the BRD4 structure from PDB, the 3-MXF, and we actually succeeded in doing a protein-protein docking of BRD4 and RNF 114. Obviously, it gave more than 10,000 binding models that generated very classical protein-protein docking. We are not using the script here yet. Okay, so we clustered that, and then based on that, to cut a long story short, we could finally get a binary complex that was actually that seemed like, and it was by visual examination. Okay, that seemed like it could actually bind the the PROTAC, because you see the individual ligands were actually this is actually showing you through the arrows the individual ligands, and you could imagine that linker could actually connect both of them. The exit vectors were right, the linker length would be right. So we took these kind of around 5 different binary complexes, and we actually optimized them a little bit more through molecular dynamics simulations using OpenMM, and then we came up with the to predict a binding mode for the PROTAC. So this is a retrospective study where we tried to just show a binding mode. You can ask me, why did you do it? Okay, we are just generating a case study. Okay, and this was done maybe about 3 years back, and Hemant presented it in the Dana-Farber targeted protein degradation. There was a trainee talk, and he presented it. We got acclaim from none other than Jay Bradner for that. Okay, so that was good. Okay. So obviously these are some of the ways you try to generate case studies and then understand, because as a modeler for you, you need to be able to explain the existing data so that you can model in a prospective manner, right? We also in similar way we have modeled both ARV 110 and the other one, I think this is the androgen receptor degrader, the estrogen receptor also we have modeled. Androgen receptor is very close to me because there is no antagonist bound structure for that. Okay, so in this particular case, when it actually took quite a bit of effort to generate that kind of a structure with the helix 12 flipped out so that this guy, the exit vector was actually following that way. So to model that, to coax the compound into that particular one, and then take the exit vector out of that and then create this whole thing. And since the experimental structure is not yet reported, we are still right. Okay? So thank you for your attention. This is a short talk. I think I didn't keep you too hungry, I hope.
Please join me in giving Dr. Ramesh a warm round of applause.